Okay, we made a start on the second one. This time we're dealing with not a surplus of electrons in the picture. This time we're dealing with a deficiency in electrons. Notice that we have each time you have 1, 2, 3 pi bonds. So each of the resonance structures we're going to draw, unless there's special circumstances and maybe a minor contributor popping up, most of the time we're going to draw resonance structures with exactly 3 pi bonds and no lone pairs shown. Okay? Remember, each of the resonance structures normally, the number of lone pairs and pi bonds is usually the same throughout every single structure, just like that last one we looked at. Okay? So, draw a second molecule, it's framework. So how are things going to be different? Well, if we are lacking electrons here, because of an empty sp2 hybridized atom, the only place we can get electrons from is this pi bond here. So a pi bond pivoting from this carbon, which is connected to both the other carbon in the pi bond and the electron deficient carbon, that bond is going to swing like a gate and pivot from that point. So the pi bond swings round like this. It's the only thing that can happen. To help with electron deficiency here, it can only use electrons connected to its neighbouring atoms. Electrons down here, are not directly connected to that carbon. They can't help. So a new structure that we draw, we have a double bond there. We'll change there, we'll change there. And then because the pi bond is broken away from this carbon, plus charge is there. Then there's a carbon to hydrogen bond on this molecule as well. And that still only gives the carbon 2, 4, 6 electrons, 3 electrons under its control, making it positive. Moving to the next picture. Again, getting help from its neighbour. Now this pi bond can pivot like a gate and swing round to plug in that gap. Again, when the pi electrons break away from that carbon, it leaves it with an incomplete octet. Same trick again. Swing those electrons around from the next pi bond. The last picture, swinging those pi electrons one last time. there's 5 resonance structures in all. Note that this one is different from the first one because the alternating pi bonds are on the opposing carbons. So it's not the same resonance structure. Look at the first structure. We have a positive charge in this corner. There's nothing to help us on this side, no lone pairs, no pi bonds connected. So the cavalry is coming from this left side. And that pi bond swings around, pivoting from that point, form a pi bond with the adjacent 2 carbon atoms. So whenever that bond swings like that, one of the atoms in the new bond is the atom which was in the original bond. Okay, swinging like a gate. So the structure we can draw now, that bond hasn't moved up there. We've moved the bond in there. And the positive charge is popped around there. Again, the electron is missing from this outer shell. His neighbour can help out once more. On the new pi bond there. Just swinging that bond around like a gate. We do have one last option. Because when we think about this nitrogen, what do we know about the combination of hydrogens and lone pairs on the hydrogen? The electrically neutral. So 3 bonds and 1 lone pair. It's the only one it fits. If it was 2 hydrogen bonds, then that nitrogen atom would be positively charged, yes. It wasn't. And if it was, instead, if it was 2 lone pairs, then the nitrogen atom would have a charge of -1. And it isn't -1 either. So, the only option is a combination of the 2. Lone pair and a nitrogen to hydrogen bond. That's the only combo that makes a nitrogen electrically neutral. So our last step, unorthodox compared to the others, is using that lone pair to make the new pi bond. The final structure now that is a breakaway from our original ones, because now we've gone up to 3 pi bonds. So it's not as regular and systematic as the other ones were. Now nitrogen in the process has gone from sp3 hybridized to sp2 hybridized. Change in hybridization to make that structure happen. So our hotspot this time are 1 pair of electrons making a negative charge in the carbon. So we need to move those electrons on. Can we go in this direction? No. Because here we already have 2 carbon to hydrogen bonds making up the octet. We're not going to break up the connectivity of the molecule. We're not going to break any existing sigma bonds. So that's a no-go. And the electrons have to move in this direction. Be careful with your arrows. If they're going to form a pi bond, make sure the arrow is between the 2 carbon points. Don't point the electrons to a carbon apex if the electrons are not going to become a lone pair on that carbon atom. That causes a bit of give. That pi bond has to move next door. So our new suitable picture just like that. Next one, again, that hot potato moving around. One pair of electrons will become a new pi bond. Has to be with an atom that the carbon's already connected to. Comes in, octet will be broken there, so that pair of electrons has to move back into being a lone pair on the oxygen. Still a combination of 3 pi bonds and 3 lone pairs in total on the structure. And that's the end of the row. We bring that lone pair back in, it has to be this pi bond that breaks, retreating back to this position. We've already got that structure on the board. There's nothing that can be done involving this last pi bond in the bottom right hand corner. Okay. Which of these 2 molecules do we believe will be more stable?
The one with first order resonance structures.
Aha, this first one. So this first molecule will be more stable because we can produce resonance structures for it. This one here, positive charge. There's already an octet here, so this pi bond really can't move anywhere. So it can't move in there, there's already an octet. So there's nothing to help that charge on the end carbon. Here, we can have the pi electron swing in to give us resonance. An alternative structure, which looks like this. The more resonance structures you can draw, the more stable this compound probably is. Resonance means lower energy. Because atoms are sharing that heavy burden of charge, lightening the load.